Let's get going. Now I'm going to talk about heat equation solution. After setting the initial heat values, we can solve the heat diffusion equation. As you can see, time derivative is a linear combination of second order special derivatives, which is therefore called the diffusion equation. And we should convert it to a difference equation in order to solve it. The resulting difference equation, I will skip the details, and the resulting difference equation can be represented as a 5-point stencil operation, because as you see, the difference equations has values from previous row and columns as well as the next rows and columns. As you can see, the stencil only needs values of delta x, delta y, and delta t, because we have Rx and Ry. Therefore, we need only delta t, delta x, and delta y values to calculate this stencil matrix, which is actually a collection of parameters to be used in the difference equation. And yeah. The important value here is the value of value at time n+1 at a point only depends on the values at time n. Yeah, that is important because that makes the problem easily parallelizable, because the previous heat values are used to calculate the new values independent of other heat values calculated for time n+1. Therefore, this is a good candidate problem to parallelize. Yeah, each point on the grid can be updated independently. Secondly, each heat point is separately calculated by a thread using each heat point can be calculated using Frobenius inner product. It is just element-wise multiplication of two matrices, stencil matrix and the data matrix, and yeah. Unfortunately, this is there's a mistake. This should be on the boundary condition, not the data, but there's a mistake, I think. Yeah, stencil matrix is used to calculate the next heat at each point, and we are using just element-wise multiplication and a sum. It is a convolution operation. Actually, in convolution, S matrix is inverted, but here we don't invert, but data processing engineers usually call this convolution, but for a mathematician, it is not convolution. Yeah, and For example, another thread will calculate the next heat value by element-wise calculation of these two matrices. And this goes like this. The whole data domain is scanned with this stencil. It's a kind of filter to calculate the next heat value. The whole grid will calculate the next heat value for the whole domain. This is important. The kernel is going to run only for one time step, and we need to run the kernel. If we need to run many steps, we need to run the same kernel many times to calculate the next step in the heat equation. Yeah. Yeah, but for our solution, we designed a stencil kernel and a border kernel. Border kernel will only run on borders, and our stencil kernel is expected to run only core nodes. Yeah, the work division can be calculated by setting grid thread extents to nodes domain. Yeah, grid thread extent, what will be the grid size? And it can be the nodes domain, all nodes or all the data domain is going to be the grid thread extent of the work division. And yeah, work division for borders kernel would need larger extents, of course, because there is a border region. But I mean, in the hands-on, we are not going to write it. A complete heat equation solution has these steps. We are going to initially define the host device and accelerator device. The host and device, in short, we can call them the host and the device, but both of them actually devices. And initially, we set the initial conditions and boundary conditions for the buffer. We did in the previous hands-on. Then we are going to copy the initial conditions to the host, of course, and we need to define the parallelization strategy, which is the work division. Then we are going to run the kernel in a loop, because we need to run not only one time step, we need to calculate the heat after, let's say, n steps. Therefore, we are going to run stencil kernel for a grid to calculate next step, and this will be called in a loop. And we are using actually two buffers in the ACC side. Let me explain you here why we are using two buffers. We are initially going to allocate a current buffer and the next buffer in the ACC GPU, allocate memories for them. And in the first calculation, we are going to, of course, in the first kernel call, we are going to fill the initial conditions we did already. But what will we do inside for loop? Inside for loop, we are going to calculate using the previous heat values, the next heat values. Each kernel will, each thread will calculate a point, and the whole grid will calculate the next heat value for the whole domain, and this will be written to another buffer. And for the next step, we swap the pointers, just change the addresses the pointers show, so that for each step we will start from the already calculated data to calculate the next heat value. This is a simple trick to use less memory in the ACC. We always use two buffers. We always take the current buffer, then calculate values and write them to another buffer. Then afterwards, we swap pointers so that again a buff curve, again the current pointer will be used as a basis to calculate the next. Then at the end, of course, the latest data is copied back to the host. This is our strategy. And here you are expected to write the stencil kernel. Actually, this calculation should be done for each thread. Thread indexed with I and J should do this calculation. It is element-wise matrix multiplication then sum. And yeah. Okay, this is enough, I think. Maybe you can continue.